Hi everyone, and welcome back to another AP Calculus video. Today we're going to talk about relative rates of growth. And really what this is it's kind of an extension of this L'Hopital's rule that we've been talking about in a previous video. So when we talk about relative rates of growth, we're talking about comparing two functions to see which one grows faster or slower than another. And the way that we do this is we take the two functions and we create a ratio. Remember, a ratio is just a fraction. So we're going to put one function compared to another. And it doesn't matter which one we put in the numerator and which one we put in the denominator. So let's take a look. And the idea is we're saying, hey, as x gets sufficiently large, in other words, as x is approaching infinity, it's getting bigger and bigger, we're plugging in bigger numbers, both of these functions will tend to infinity. But as we've said in the previous video with L'Hopital's rule, not all infinities are created equal. And so one function may just grow faster and larger and approach infinity much faster than the other. And I think you can get a sense here, e to the x, anytime we have an exponential function, that's going to grow way faster. You know, this harkens back to that old algebra problem where we said, hey, at Christmas break, would you rather earn $1 a day, or would you like to have your money doubled? I'll give you a penny and you can double your money. Well, at some point, the exponential, when we double our money, it catches up to that $1 a day. And as, you know, the days go on to infinity, that exponential function, you're just going to be doubling and doubling and doubling. You'd much rather have that than the slow and steady growth of having, you know, just adding $1 each day. So similarly, we have x squared and e to the x. We have x squared, which is, you know, a polynomial function. And then e to the x are exponential. So I'll tell you right now, e to the x is going to grow faster. And I hope that you have a sense of that. So let's see how we do this. What we do is we say, you know, remember, anytime we're talking about faster or slower, we're talking about derivatives. We're talking about which derivative is greater than the other. Because the derivative is really, that's the rate of change. So if one derivative is bigger than the other, well, then clearly it must be the faster function. So we're going to use L'Hopital's rule to compare the derivatives. And essentially what we do is we say, okay, if I'm going to call this function e to the x, then, or sorry, this function f of x, then I put it right here in the numerator. If I call this function g of x, I'm going to put that in the denominator. And like I said, it really doesn't matter which one goes where. So then we evaluate the limit. So here's how it kind of works out. We're going to say, well, we know that when we deal with this, we're going to get kind of that infinity over infinity situation, which we're going to put an x through right away, because we never say it equals in indeterminate form. We always put an x over it. So then I'm going to say, well, the limit as x approaches infinity of e to the x equals infinity. The limit as x approaches infinity of x squared equals infinity. And I'm going to then do my derivatives. Oops, I'm going to use L'Hopital's rule. So I'm going to say the limit as x approaches infinity, e to the x over 2x. Well, the same thing is going to happen again. And generally speaking, when we use L'Hopital's rule, we want to make sure that each time we are saying this. So, you know, this, we get infinity over infinity again. So we're going to cross it out. We're going to give the reason why we're able to use L'Hopital's rule again. And then we're going to use L'Hopital's rule. So we're going to do the derivative again. We're going to use repeated L'Hopital's rule. Well, now we get infinity. Now, what does this mean? What this means is that when I'm dealing with this function, as I've done the derivative, the rates of change, the rate of change of the top one is infinitely larger than the rate of change of the bottom one. The rate of change of the bottom one eventually goes to 0. The rate of change of the numerator is much larger. So when we compare these two things and we get infinity, what that means is the numerator is growing exponentially faster in this case than the denominator. It's not always exponentially faster, but here it is. And what this tells me is that whatever value I had on top, that's the faster function. That one's growing faster than the other one. When I get infinity as a result, the numerator is growing infinitely faster than the bottom. So what this says is that, oh, e to the x grows faster than x squared, because that was what was on the top. Now, what happens if I switch them? Well, let's take a look. If I switch them, And I'm going to just kind of jump ahead. I'm going to skip ahead to, I know I'm going to get 0 over 0. So I'm going to go ahead and just do L'Hopital's rule here. And I'm going to have to do it again. And, you know, for these types of problems where you end up doing L'Hopital's rule over and over again, very rarely do these things show up on like an AP exam. More than twice, it's probably a multiple choice question. You don't have to like state those little things. But in general, on a free response, you're going to you have to, or you don't get credit for L'Hopital's rule. But essentially what we do here is we get 2 divided by a really big number, which is 0. So you end up getting 0 as your limit. Now, what does this tell me? This tells me that the top function got super duper small, and when I take a super duper, you know, comparatively speaking, when I take a smaller number and divide it by a much, much, much larger number, I get 0. So this tells me whatever I'm dividing by is just getting ginormous compared to the numerator. So when you think about the number sense behind this, it makes sense that when I get infinity as my result, when I compare them, whatever was on the top is the faster function. When I get 0, whatever's on the bottom is the faster function. It means it's getting bigger quicker than the top one. So when you have, you know, it's still going to be a big number, but divided by an even bigger number, that limit of that ratio is approaching 0. So if you kind of have this number sense about it, when I get 0 here, it means the bottom function was growing faster. So we get the same result with different values depending on how we put the function. So it really does not matter which one goes in the numerator and which one's in the denominator. So let's kind of sum up what we've just figured out. And there's one more scenario that we're going to add to our notes. So what do we deduce based on the observations? When our limit as x approaches infinity of f of x over g of x was infinity, that means the top is faster. When this one equaled 0, that means the bottom was faster. So remember, think of it like this. When you get infinity, it means whatever's on top is so ginormous that it's just swallowing up that bottom function. When you get 0, it means that the top is so small compared to the bottom. The bottom just is growing so fast that you're dividing a small number by a ginormous number. That value approaches 0. So here are the 3 scenarios that we just kind of talked about, and you might want to pause it and copy a couple things down. It says this: let f and g be positive. So we have to have functions that are positive. If we have negative functions, then it gets weird. But when you're comparing 2 positive functions for x sufficiently large, in other words, as x approaches infinity, that's what it means to be sufficiently large. Case 1, we say that f grows faster than g if the ratio, if f is in the numerator and you get infinity, or if f is in the denominator and you get 0. We say g grows faster if f over g yields a limit of 0, or if g is in the numerator, you get infinity. So kind of what we just said, it's just saying it in a less nice way. Now the third scenario that you could get is a number other than 0. So when you get this limit and it equals L, what that means is that the ratio of the rates is a constant other than 0. So you might get like 2 or 1. And what happens is when that happens, when you get a number not 0 and not infinity, it means that they're growing at relatively the same rate. You'll often get this scenario when you compare like you know, two polynomials. So like, for example, if you wanted to do the limit as x approaches infinity, where one polynomial is x squared plus 1 and the other polynomial is 3x squared plus 1. Well, when you evaluate this, you end up getting 1/3. So that means they grow at the same rate. They're both quadratic functions and they grow at the same rate. In the long run, when x is super duper big, multiplying it by 3 isn't going to do much to it. When squaring it, that's going to do something to it. But multiplying it by 3, you know, we're talking about like quadrillions and, you know, infinite values. So let's take a look at some examples. We're going to compare these two and see which grows faster. You might want to pause and just try this setup on your own. Otherwise, you can stick around and just watch me do it. So I'm going to set this up. I'm going to do the limit as x approaches infinity of the natural log of x over x squared. I'm just going to choose one to go on the top. And when I do this, I get infinity over infinity. So with these, I'm actually not going to state my reasons for using L'Hopital's rule. I'm just going to kind of use it. So I'm going to have 1 over x over x squared, which is going to be 1 over x cubed, which is 0. So when we get 0, it means that the bottom is ginormous. So you're going to have like something divided by a really big number. So that means the bottom is faster. So when you get 0, it means the bottom is faster. So then I'm going to go back to where I had my initial setup. See what I put in the bottom. So x squared grows faster. So let's keep going. Let's try another one. And like I said, you can pause the video at any point in time and, kind of compare. Let's get crazy. Here we go. The limit as x approaches infinity. Put something in the top. Oh, yikes. All right, well, here we go. I know I'm going to get infinity over infinity, so let's kind of talk about what's happening here. When I try to do my derivatives, here's kind of what's going to go on. I'm going to get this. I'm going to get the limit as x approaches infinity. I'm going to have like 1/2 x squared plus 5 to the negative 1/2 times 2x. And I'm just going to have square roots. And here's the problem with square roots. You just can't get rid of them. This is just going to be ugly. And you're going to have square roots. Just think about it. That right there is going to become x to the negative 1/2 power. And you're going to have square roots inside square roots. And then if you do the derivative again, it'll turn into like a 3/2 power and then a 5/2 power because you keep subtracting 1, but it's always going to be a square root. And you'll never be able to get rid of the square root. So one thing we do is when we have square roots and square roots, square root in the f function and square root in the g function, what we do is we have to get a little crazy and get a little, creative. And think of it this way. If I wanted to see who runs a race faster, me or you, and we're not actually able to race each other. For whatever reason, we just can't race each other. But I know that I run faster than Mike. And if I run faster than Mike, and then Mike runs faster than you, then if Mike is faster than you are, and I'm faster than Mike, well then I know that I'm faster than you. And that's called the transitive property. And what we can do here is instead of saying, well, who's faster or slower, what I can do is I can say this. I can say, well, let me find a function that grows at the same rate. And I can show that two functions kind of grow at the same rate. It's another way to think of this is if I run a mile in 10 minutes and Mike runs a mile in 10 minutes, and you and Mike run the mile at the same time, then I can deduce that you must run your mile in 10 minutes. So it's this transitive property of bringing in a third function and just using that for comparativeness. So if f grows at the same rate as g and g grows at the same rate as f, then f and h must grow at the same rate. So there you go. So let's try this crazy example again with the square roots. We're going to compare to x. Now, here's why I chose x. When I look at the overall behavior of the function, I'm going to look at the leading term. And I'm square rooting x squared. So essentially, the end behavior model for this would be x. Oh. And really, this guy, because I'm squaring everything, and no, I'm not going to do that. I'm going to just square the leading term. The end behavior model becomes 2 square root of x squared, or 2x. So what I really want to do here is I want to get to the root of what's the leading term, because the leading term really drives the function. All the other things, that plus 5, when we're talking about infinities, that's nothing, right? So you have the square root of x squared. The end behavior model is just that leading term. And what I want to do here is I want to compare to the end behavior model. And if both functions have a similar end behavior model, that's what I'm going to use to compare to. So I'm going to compare to x because they're both going to behave like a linear function in the long run. So let's do this. Let's do the limit of, let's see, the square root of x squared plus 5 over x as x approaches infinity. Now, before I start, going all crazy with this, I'm going to show you guys just a little trick that I know with limits. Now, if there's one thing that you need to be taking away from these videos, it's this. When I have square roots inside limits and I try to use L'Hopital's rule with anything involving a square root, it's just not going to go well. So I need to find other ways to kind of manipulate my way through this. And you can try to use L'Hopital's rule for this, and it's just not going to go well. It's going to be ugly. So what I'm going to do is I'm going to say, well, I'm going to rewrite this x. I'm going to rewrite it so that it matches kind of the function that I'm dealing with. And it looks like this. I'm going to rewrite x as the square root of x squared. Oh, look, it's the end behavior model. Oh my gosh. And then this allows me to put it all together like this, which then allows me to do this. I'm going to divide everything by x squared. I'm going to get 1 plus 5 over x squared, which then turns into the square root of 1 plus 0, or the square root of 1, which is 1. Oh, so these two functions do grow at the same rate. They're end behavior models. We would expect this. So the next thing I'm going to do, so h of x and f of x grow at the same rate. Now let's compare h and g. I'm going to do kind of the same thing. So here we go. I'm going to have the limit as x approaches infinity. I'm going to have 2 square root of x minus 1 squared over x. Now, same problem. I'm going to have square roots. Can't L'Hopital my way out of square roots. Square roots, bad news bears. But what I can do is I can reframe this x, and it looks like this. I'm going to go back up here to this end behavior model. I'm going to write it as the square root of x squared. Now both of them have the same exponent, so I'm going to combine them. And I'm just going to keep simplifying my way through this. So I'm going to write this as 2 square root of x over the square root of x minus 1 over the square root of x all squared. These are going to cancel, so I get the limit as x approaches infinity of 2 minus 1 over the square root of x squared. When I put infinity in, this term goes to 0, so I'm going to get 4. Oh, that's okay. Good deal. So when I am dealing with this, I get that g and h grow at the same rate, and then I get f and h growing at the same rate. And because f grows the same as h and h grows the same as g, therefore, by the transitive property, f and g must also grow at the same rate. So I would simply write that out. Since f and h grow at the same rate, and G and H grow at same rate, F and G grow at the same rate by the transitive property. You don't have to say that's by the transitive property. So there you go. That's that transitive property, and that's how that's going to work for those relative rates of growth. And that's how we choose that third function. Now, you're not always going to be forced to choose that same function, and sometimes you'll just be given a function like in your homework. It might just say, hey, use this third function and use that transitive property. Well, then it's given to you just like it is here. But if you ever have to decide on one, try to stick with this concept of using the end behavior model. So look at the leading term. It's the square root of x squared. Don't look at the rest of them. Look at the biggest exponent. That's going to really drive the behavior. And it'll help you determine what that function is that you can use for that transitive property. This is the sort of thing that's just going to come with practice. And, you know, these are problem-solving things. And this is just one of those things where you may or may not be successful at every little thing that you try. And it's only going to be through conversations with other people that you're going to be exposed to what other people are thinking. It's kind of like this. When you wake up in the morning, your thoughts are driven by, you know, things that are happening in your life. And we all have different circumstances. We're all coming from different places. So the creativity that is needed for coming up with these sorts of things really is driven by what's going on inside of our brain. And since we're all coming from different places, when we come together, it's really important to be able to talk to one another and to pick each other's brains, especially for these creative things. Because there's often more than one way to solve a problem, and you may not think of it because your experiences that day haven't opened your mind to being able to consider the problem in different ways. And that's okay. We're all coming at it from different angles. But when we come together as a team and we talk about it and we have a conversation about these problems and we share our ideas and we ask each other questions, well, then we can be exposed to the different ways of thinking that people are bringing to the table. So my encouragement to you is that as you approach these problems, if they're tricky, reach out to a friend. Ask a friend how they did it. Look it up online. Learn from the things that other people are doing so that you can expand your mind and you can be exposed to the different ways to solve the problems. And when all else fails, you can always come to me for help. I'm more than happy to talk you through it. But we're getting into this realm of problem solving and unique types of problems where conversations are really going to be the best way and the best tool for learning. So keep at it. Do not be afraid to reach out when you have questions and to seek the advice and the mindset and the creativity of others. Because where you might need help on a problem like this, there's going to be someone else who needs help on a problem that you've got down, because that's where your mindset is. And when you woke up that day, that's the direction your mind was able to go. So different angles, different backgrounds, different ways of approaching problems. We all need to come together so that we can all grow better at this. So keep practicing, keep at it. You can do this. You've got this.